In 1805, Carl Friedrich Gauss wrote down an algorithm that could have changed the trajectory of nuclear weapons. He never published it. In 1952, a woman named Rosalind Franklin pointed an X-ray beam at a strand of DNA and captured a photograph that was, mathematically, a frequency decomposition of the molecule of life. She died before anyone gave her credit. And right now, in the device you are holding, an equation written by a man who nearly lost his head to the guillotine is executing thousands of times per second to deliver my voice to your ears. These three facts are the same story. They share one equation written by an orphan in 1768, rejected by the most powerful mathematician in Europe, suppressed for 15 years, and now running tens of trillions of times per second on every connected device on the planet. Tonight, we trace the line from that orphaned stolen candlelight to the inside of your phone through a Cold War nuclear gambit, a stolen photograph of DNA, and a question about reality that quantum mechanics answered decades ago and nobody wanted to say out loud. Get comfortable, subscribe, or join if you have not. And if you want more of this across physics, math, and the buried parts of science, the Patreon is where those deeper threads live. Stay to the end, because this one lands somewhere you are not expecting. Let's start where it started. Right now, in the time it takes you to finish this sentence, something on the order of 10 trillion mathematical operations just executed across the surface of the Earth. Not additions, not multiplications. One specific operation derived from one specific equation written by one specific man in 1807. That operation is running inside the phone in your pocket. It is running inside every Wi-Fi router in your building. It is running inside the screen you are watching this on right now, decoding the compression algorithm that is delivering my voice to your ears. It ran inside the MRI machine that last scanned someone you love. It ran inside the gravitational wave detector that heard two black holes collide 1.3 billion light years away. It ran inside the satellite that told your GPS where you were this morning. It is running inside every cell tower, every digital radio, every noise-cancelling headphone, every streaming service, every radar installation, every hospital imaging suite, every seismograph, every voice assistant, and every single video call happening anywhere on the planet at this moment. And the man who wrote it was a 9-year-old orphan from central France who should not have survived long enough to pick up a pencil. His name was Jean-Baptiste Joseph Fourier, born March 21st, 1768, in Auxerre, the 9th of 12 children of a master tailor. His mother died when he was 9. His father died a year later. By the time most children are learning long division, Fourier had no parents, no money, no family name of any consequence, and no realistic path to anything other than manual labor or the church. The local bishop took pity on him and placed him in the École Royale Militaire of Auxerre, a military school run by Benedictine monks. And something happened there that the monks did not expect. The boy became obsessed with mathematics. Not interested, obsessed. He would collect the wax drippings from used candle ends, the scraps the other students threw away, melt them together into crude stubs, and use them to study alone in empty classrooms, long after everyone else had gone to sleep. By the age of 13, he had worked his way through all 6 volumes of Bezout's Cours de Mathématiques, a graduate-level text. By 14, he was solving problems that his teachers could not. And then France told him it did not matter. He applied for a commission in the artillery, the branch of the military where mathematical talent could actually be used, and was rejected. Not because his work was insufficient, not because his grades were poor, because he was the son of a tailor. The commissions in the scientific corps of the army were reserved for those of noble birth, and Fourier, regardless of what he could do with numbers, was not noble. One account, repeated across multiple biographies, records that he was told he could not enter the artillery even if he were a second Newton. Think about that for a moment. A child orphan, studying by candlelight, he had to scavenge from garbage, solving mathematics beyond his instructors, and the system looked at him and said, "You are the wrong kind of person for this to count." So he did what orphans with no options do. He prepared to become a monk. He entered the Benedictine Abbey of Saint Benoît-sur-Loire in 1787, intending to take his vows and disappear into a life of prayer and silence. Mathematics would have been a private hobby. The equations would have stayed in his notebooks, unread, unpublished. The single most consequential mathematical idea of the next 2 centuries would have died in a monastery. But then the French Revolution happened, and it saved his life by nearly ending it. I need to pause here because I want you to understand something about what is coming. The equation Fourier eventually wrote, the one that is running trillions of times per second on every connected device on this planet, did not come from a moment of serene genius in a quiet study. It came from a man who had been orphaned, rejected, nearly executed, dragged across a desert by Napoleon, and publicly humiliated by the most powerful mathematicians in Europe. And when he finally presented it, the establishment told him he was wrong. They suppressed his paper for 15 years. He died before seeing it fully vindicated. And here is the part that should disturb you. He was technically wrong. The broadest version of his claim, the one that Lagrange attacked, the one the committee refused to publish, contains a mathematical error. But the thing he was wrong about does not matter. What he was right about is so fundamental, so deeply woven into the structure of reality itself, that 200 years later, it is running inside every piece of technology you own. It underpins the quantum mechanical description of matter, and it may be the single best clue we have about what the universe actually is at its deepest level. And nobody talks about it. Not like this. Not about what it actually means. You learned about Fourier in a math class, if you learned about him at all. You were shown the equation, maybe asked to compute a few coefficients, told it was useful for signal processing, and moved on. That is the safe version, the version that treats Fourier analysis as a tool, like a wrench or a calculator, something engineers use, something practical. What Fourier discovered in the back rooms of a prefectural office in Grenoble, while simultaneously draining swamps and managing Napoleon's provincial bureaucracy, is that reality has a second face, that every signal, every vibration, every phenomenon that changes over time or space, no matter how complex, no matter how jagged, no matter how apparently random, is actually a sum of pure, smooth, perfectly predictable waves. That the complexity you see is a surface illusion. Underneath it, everything is frequencies, and the equation he wrote is the key that translates between the 2 versions of the world. The version you see and the version that is actually there. That is not a tool. That is a statement about the architecture of reality and the reason it works inside your phone and inside a gravitational wave detector and inside the equations of quantum mechanics is not because engineers found a clever application for old math. It is because Fourier stumbled onto something true about the universe itself, something that was already there, waiting in the structure of matter and energy and information long before human beings existed to notice it. And the story of how that happened, the story of the orphan and the revolution, and the guillotine, and the desert, and the ambush at the Institut de France, and the death on a staircase, and the lost manuscript that set mathematics back by 16 years. That story has never been told the way it needs to be told, because telling it properly means following the implications all the way down, past the engineering applications, past the signal processing, past the compression algorithms, down to the level where you have to ask a question that physicists do not like to answer. Is the world made of things, or is it made of frequencies? And if the answer is frequencies, then what exactly are you? We are going to find out. And it starts in 1789, in a country that has just decided to cut off the heads of everyone in charge. The revolution freed Fourier from his monastic obligations. The Constituent Assembly passed laws in 1789 forbidding the taking of religious vows, which gave him a legal exit from Saint-Benoît-sur-Loire. He returned to Auxerre and took a teaching position at his old military school, now reorganized under revolutionary governance. And then he did what many intelligent young men in revolutionary France did. He got involved in politics. He joined the local revolutionary committee, became its president in 1793, and threw himself into the cause with the same intensity he had once directed at Bézout's textbooks. This nearly killed him. In the summer of 1794, Fourier was arrested. The charge was that he had defended a faction in Orleans associated with the Hébétists, a radical group that had fallen out of favor with Robespierre's Committee of Public Safety. In revolutionary France in 1794, falling out of favor with the Committee of Public Safety meant one thing: the guillotine. Fourier was imprisoned, and according to multiple biographical accounts, his execution was scheduled. The man who would write the equation that runs the modern world was sitting in a cell waiting to have his head removed because he had backed the wrong political faction in a provincial dispute. He was saved by an accident of timing that is almost too absurd to be real. On the 28th of July, 1794, Robespierre himself was arrested and executed. The reign of terror collapsed overnight. The political winds reversed. Fourier's death sentence evaporated, not because anyone reviewed his case or determined his innocence, but because the man who had ordered his death had his own head cut off first. But Fourier was not done being nearly killed by French politics. After the Thermidorian reaction that followed Robespierre's fall, a new faction seized power, and they arrested Fourier again, this time for his association with the revolutionary committee he had once led. He was imprisoned a second time, and a second time he was saved, this time by appeals from his students and from three men whose names you will recognize if you have ever opened a calculus textbook: Joseph-Louis Lagrange, Pierre-Simon Laplace, and Gaspard Monge all intervened on Fourier's behalf, arguing that France could not afford to execute its mathematicians. He was released. Remember those three names: Lagrange, Laplace, and Monge. They saved his life in 1794. 13 years later, two of them would try to destroy his life's work, and the third would watch it happen. Fourier landed on his feet. He was admitted to the École Normale Supérieure in Paris, then appointed to the faculty of the École Polytechnique, where, in 1797, he succeeded Lagrange himself in the chair of analysis and mechanics. The orphan from Auxerre was now occupying the most prestigious mathematics teaching position in France, a chair vacated by the most famous mathematician in Europe. And then Napoleon came calling. In May of 1798, Fourier sailed with Napoleon's expedition to Egypt, not as a soldier, as a scholar. Napoleon, whatever his many faults, understood the propaganda value of science, and he organized the Institut d'Égypte as a cultural research body to accompany the military campaign. Fourier was assigned to the mathematics section, of which Napoleon was himself a member, and eventually became the Institute's permanent secretary. He organized archaeological surveys, catalogued artifacts, and managed the administrative machinery of a military occupation, while simultaneously working on mathematics in the Cairo heat. And the Egypt years changed him, not just intellectually, but physically. Fourier developed a heart condition, possibly an aneurysm, during the campaign, and he developed something else, something that biographers have argued about for 2 centuries, an obsession with heat. After his return to France, Fourier kept his rooms so hot that visitors complained they could barely breathe. He wore heavy coats, even in summer. He wrapped himself in blankets. His biographer John Heravel, in the 1975 book Joseph Fourier, The Man and the Physicist, suggests the habit was partly medical, a response to genuine cardiovascular disease from the Egyptian climate. But the symbolism is impossible to ignore. The man who would write the equations of heat conduction could not stop surrounding himself with heat, as if he were trying to solve the problem with his own body, before he solved it with mathematics. In 1802, Napoleon appointed Fourier prefect of the Isère, a department centered on Grenoble, at the foot of the French Alps. It was an administrative position, not an academic one. Fourier was now responsible for roads, public health, tax collection, and civil order. And he was very good at it. He drained the swamps of Bourgogne, which had been breeding malaria-carrying mosquitoes for generations, ending seasonal fever epidemics that had plagued the region for decades. He planned the road from Grenoble to Turin. He was made a baron in 1809, and the whole time, in whatever hours remained after the bureaucratic work was done, he was working on the problem that had consumed him since Egypt. How does heat move? Not metaphorically. Physically, if you heat one end of a metal bar, how does the temperature distribute itself along the bar over time? What is the equation that governs the flow of heat through a solid? This was not a new question. Newton had proposed a law of cooling. Other mathematicians had chipped away at special cases, but nobody had solved the general problem. Nobody had written a differential equation for heat conduction and produced a general method of solution. Fourier did, working alone in a prefectural office in Grenoble, managing Napoleon's provincial administration by day and wrestling with partial differential equations by night. He derived the heat equation and developed a method of solving it that required something nobody had ever seriously proposed before. He claimed that any function at all, continuous or discontinuous, smooth or jagged, periodic or not, could be written as an infinite sum of sine and cosine waves. Any function, no exceptions. That is the claim that would change the world. That is the claim that Lagrange would call impossible. That is the claim that the Institut de France would suppress for 15 years. That is the claim that was, in its most absolute form, technically wrong. And that is the claim that is, in every way that matters, the most correct and consequential assertion in the history of applied mathematics. On the 21st of December, 1807, Fourier traveled to Paris and read his memoir on the propagation of heat in solid bodies before the Institut de France. The committee appointed to evaluate his work consisted of 4 men: Lagrange, Laplace, Monge, and Lacroix. 3 of the 4 had saved his life 13 years earlier. Now they sat in judgment of his mathematics. And what happened in that room was an ambush. Lagrange had spent nearly 50 years, half a century, insisting that arbitrary functions could not be represented by trigonometric series. This was not a minor technical opinion. It was a pillar of his mathematical worldview. Lagrange had been involved in the vibrating string controversy of the 1750s and 60s, a decades-long argument with Euler and D'Alembert about what kinds of functions could describe the motion of a plucked string. And Lagrange had concluded, firmly and publicly, that a sum of sines and cosines, being smooth and analytic, could only represent smooth and analytic functions. You could not, he argued, build something jagged out of smooth parts. You could not construct a discontinuous step function from perfectly continuous waves. And now here was Fourier, a provincial prefect, not a professional mathematician, standing before the most powerful scientific body in France, claiming that Lagrange was wrong, claiming that you could write any function, including discontinuous ones, including step functions, including things with sharp corners and sudden jumps, as a sum of sines and cosines, claiming in essence that smoothness could produce roughness, that order could generate chaos, that the simple could encode the complex. Lagrange exploded. He objected formally. He objected repeatedly. He refused to accept the central claim. And because Lagrange was Lagrange, because he was the most respected mathematician in Europe, because his word carried more weight than anyone else's in that room, the committee followed his lead. While Laplace and the other reviewers were inclined to publish, Lagrange adamantly protested, and the Institut de France bowed to his prestige. Fourier's 1807 memoir was rejected for publication, not because the heat equation was wrong, not because the solution method did not work, but because the mathematical claim that made the solution method possible, the claim about trigonometric series, violated what the most powerful man in the room believed to be true. I want to sit with that for a moment. The single most consequential mathematical idea in the history of technology was suppressed because one elderly mathematician could not accept that smooth waves could represent rough functions. The equation that now runs every screen and signal on Earth was filed away in a drawer because Joseph Louis Lagrange had spent 50 years believing something that turned out to be wrong, and he would rather kill a paper than update his understanding. That is not conspiracy. That is something worse. That is institutional inertia, operating exactly as it always operates. The most dangerous force in the history of science is not ignorance. It is the comfort of established experts who have built their reputations on a particular version of the truth and cannot afford, psychologically or professionally, to let it be revised. Fourier tried again. He expanded the memoir, added new results, new applications, and submitted it for the Institute's Grand Prix on heat conduction in 1811. This time, the committee included Legendre alongside Lagrange and Laplace. In 1812, Fourier was awarded the Grand Prix. He won, but the committee's report contained a line that has become one of the most famous backhanded compliments in the history of mathematics. They acknowledged the importance of his work, but noted that it leaves something to be desired on the score of generality and even rigor. Translation: you got the prize, but we still think you are wrong about the important part. And to make the insult complete, the prize-winning paper was not published in the Memoirs of the Institute until 1824, 12 years after the prize was awarded. By then, Lagrange was dead. He had passed in 1813, never accepting Fourier's central claim. This is the part where I need to tell you about what Fourier was actually claiming, precisely, because the details matter. They matter for the story, and they matter for what comes later, when we follow this equation into your phone and your MRI machine and the quantum mechanical description of reality. Fourier's heat equation describes how temperature changes over time in a solid object. In modern notation, it says the rate of change of temperature at any point is proportional to the second spatial derivative of the temperature at that point. What that means physically is that heat flows from hot regions to cold regions, and the rate of flow depends on how sharply the temperature changes from one point to another. It is an elegantly simple equation for an extraordinarily common physical process. But to solve it, Fourier needed to handle the initial conditions. If you heat a metal bar to some specific temperature profile, some particular shape of hot and cold along its length, and then let it evolve, you need to express that initial shape mathematically in a way the equation can work with. And Fourier's method of separation of variables naturally produced solutions that were sines and cosines. Each individual solution was a sine wave that decayed exponentially over time, each frequency decaying at a different rate, the high frequencies dying out fast, the low frequencies persisting, which, if you think about it, is exactly what heat does. The fine details of a temperature distribution smooth out quickly. The broad, low-frequency features persist longest. The equation knows this because the equation is built from waves. But for this method to work for any initial temperature distribution, for any starting shape at all, you needed to be able to decompose that starting shape into sines and cosines. And that is the claim, the Fourier series. For a function of period 2L, the function equals a constant plus an infinite sum of cosine terms and sine terms, each at a different frequency, each with its own amplitude. The amplitudes are determined by integrals of the original function multiplied by the corresponding sine or cosine. And Fourier asserted that this works for any function you can draw, any function you can physically produce as a temperature distribution, any function at all. To Lagrange, this was nonsensical. A sine wave is infinitely smooth. An infinite sum of infinitely smooth functions should be infinitely smooth. How can you add up smooth things and get a sharp corner? How can you combine continuous curves and produce a discontinuous jump? It violated Lagrange's mathematical intuition at the deepest level, and in a narrow technical sense, Lagrange had a point. There are functions, weird, pathological, specifically constructed mathematical functions whose Fourier series do not converge properly. Paul Dubois-Raymond proved in 1873 that there exists a continuous function whose Fourier series diverges at a point. So Fourier's strongest claim, the absolute claim, was wrong. And here, I want to correct a misconception that I see repeated constantly in textbooks, in YouTube videos, in popular science articles, because getting this right matters for what comes later. The misconception is that because Fourier's strongest claim was wrong, his contribution was somehow diminished, or that the controversy with Lagrange was a case where both sides had valid points, and the truth was somewhere in the middle. That is not what happened. What happened is that Lagrange was catastrophically wrong about the fundamental claim, wrong about whether smooth waves can build rough functions, wrong about the basic principle, and Fourier was trivially wrong about a technical edge case. Lagrange's objection was not a nuanced correction. It was a failure of mathematical imagination from the most prestigious mathematician in Europe. Because here is what actually happens when you build a step function from sine waves. You start with the first harmonic, a single sine wave. It looks nothing like a step function. You add the second harmonic and you get something that vaguely oscillates in the right direction. You add the third, fourth, fifth harmonics, and the approximation starts to sharpen. By the time you have 50 terms, the sum looks very much like a step function, with flat regions where the step is flat, and a steep transition where the step jumps. By the time you have 1,000 terms, the approximation is nearly perfect, except for one curious feature. Right at the discontinuity, right where the step function jumps, the Fourier sum overshoots the top and undershoots the bottom by about 9%. It cannot help it. No matter how many terms you add, that overshoot never fully goes away. It just gets narrower and narrower, compressed into a thinner and thinner spike near the discontinuity. But it never disappears. This is the Gibbs phenomenon, first observed by Henry Wilbraham in 1848 and independently by J. Willard Gibbs in 1899, and it is mathematically real. The Fourier series of a discontinuous function will always overshoot at the discontinuity by approximately 9% of the jump. But the energy in that overshoot, the total integrated error, goes to zero as you add more terms. In the L2 sense, in the energy sense, the Fourier series converges perfectly even for discontinuous functions. The overshoot is real, but it carries no energy. It is a mathematical ghost. And for physical signals, where energy is what matters, the Fourier decomposition is exact. This is what Lagrange could not see. He saw the overshoot and concluded the method failed. Fourier saw past the overshoot to the underlying truth. Smooth waves can build rough functions. The energy converges. The representation is complete. And every physical signal on Earth proves it every second of every day. But here is what matters. Every physically real signal, every temperature distribution you can actually produce, every vibration you can actually measure, every sound wave, every electromagnetic pulse, every piece of data that any instrument has ever recorded satisfies the conditions under which Fourier's claim is perfectly correct. The mathematician Peter Gustav Lejeune Dirichlet proved this rigorously in 1829, just a year before Fourier's death, in a paper published in Crell's Journal, Volume 4, pages 157 through 169. Dirichlet showed that if a function is bounded, has a finite number of extrema per period, and has a finite number of finite discontinuities, then its Fourier series converges. At points where the function is continuous, it converges to the value of the function. At points where the function jumps, it converges to the midpoint of the jump. These are called the Dirichlet conditions. And every real physical signal that has ever existed or ever will exist satisfies them. Fourier was wrong in the way that only someone who is fundamentally right can be wrong. He overclaimed. He said, any function, when he should have said, any function that describes something physically real. But the physical universe was on his side. The universe, it turns out, does not produce pathological functions. It produces exactly the kind of functions that Fourier's method handles perfectly, as if the mathematics and the physics were built for each other. As if Fourier had not invented a tool, but discovered a feature of reality that was already there. I spent an unreasonable amount of time reading the primary sources on this, and the thing that struck me is that nobody in 1807, not Fourier, not Lagrange, not Laplace, had any idea what they were actually arguing about. They thought they were arguing about convergence conditions for trigonometric series. They were actually arguing about the architecture of the physical universe, about whether reality has a frequency domain description that is just as valid, just as complete, just as real as the time domain description you experience with your senses every day. Fourier said yes. Lagrange said no. The universe sided with the orphan. But Fourier would not live to see the full vindication, and the manner of his death carries an irony so heavy it feels like fiction. By the 1820s, Fourier had finally published his masterwork. The Théorie analytique de la chaleur appeared in 1822, and it is one of the most influential scientific texts ever written. Lord Kelvin would later call it a great mathematical poem. It contained not just the heat equation and the Fourier series, but also the first quantitative argument that the Earth's atmosphere traps outgoing radiation, the first step toward what we now call the greenhouse effect. Fourier had been elected to the Académie des Sciences in 1817, and by 1822, he was its permanent secretary, the most powerful administrative position in French science. The orphan from Auxerre had climbed as high as a mathematician could climb in France, but his health was failing. The heart condition from Egypt had worsened. He was 62 years old, still wrapping himself in heavy coats, still keeping his room stifling hot, still treating his body as if warmth itself could keep him alive. And in February of 1830, a young man named Évariste Galois submitted a manuscript to the Académie des Sciences for the Grand Prix de Mathematics. The manuscript was on the solvability of polynomial equations by radicals. It contained the foundations of what we now call group theory, one of the most important branches of modern abstract algebra. And as permanent secretary, Fourier took the manuscript home to read. On the 4th of May, 1830, Fourier fell down the stairs at his home in Paris. Whether the fall was caused by his heart condition, by the heavy blankets he perpetually wrapped himself in, by simple age, the sources disagree. What they agree on is that he never recovered. He died 12 days later, on the 16th of May, 1830, at the age of 62, and Galois' manuscript was never found. I need you to understand the weight of what that means. Évariste Galois was 18 years old. He had submitted the most important mathematics paper of the 19th century to the most important scientific body in France. The man responsible for evaluating it had taken it home and died. The manuscript disappeared. It was not in Fourier's papers. It was not in the Académie's files. It was gone. The Grand Prix for 1830 was awarded jointly to Niels Henrik Abel, posthumously, and to Carl Gustav Jacob Jacobi for their work on elliptic functions. Galois' work was never considered, not because it was wrong, not because it was rejected, because the man who was supposed to read it died on a staircase, and the paper died with him. Galois, already politically radical and increasingly bitter, joined the Republican movement, was imprisoned twice, and on the 31st of May, 1832, at the age of 20, he was killed in a duel. The night before, he stayed up writing frantic letters to his friends, scribbling the outlines of his mathematical ideas in the margins, knowing he would likely die the next morning. It was not until September of 1843, 13 years after Fourier's death and 11 years after Galois's, that the mathematician Joseph Liouville announced to the Académie that he had reconstructed Galois' theory from surviving notes and fragments. It was published in his journal in 1846. Group theory, the branch of mathematics that underlies everything from particle physics to cryptography, was delayed by 16 years because of a fall on a staircase. One staircase, 2 dead mathematicians. 16 years of lost mathematics. And the statue of Fourier that was erected in Auxerre in 1849, the one that commemorated the orphan who became a baron, the man who discovered how heat moves and how functions decompose, that statue was melted down by the Nazis during World War II, turned into ammunition. The bronze that honored the man whose equation now runs every piece of technology on the planet was liquefied and shaped into bullets. If you are wondering whether there is a pattern here, whether the universe has a particularly vicious sense of irony when it comes to the people who discover its deepest truths, I have bad news. The pattern only gets worse from here, because Fourier's equation did not stay confined to heat. It escaped. It spread into every branch of physics, every branch of engineering, every branch of technology. And the story of how it did that begins with another buried discovery, another suppressed algorithm, and another case where the people who should have recognized what they had instead filed it away and forgot about it. And this time, the stakes were nuclear. To understand what happened next, you need to understand a problem, a practical, computational, unglamorous problem that would have bored Fourier to tears, and that turned out to be the bottleneck standing between his equation and the entire modern world. Fourier's equation, the Fourier Transform, is beautiful in continuous mathematics. You take a function, multiply it by a complex exponential, integrate over all time, and you get the frequency spectrum. Clean, elegant, infinite precision. But the physical world does not give you continuous functions. It gives you data, discrete samples. A microphone records a sound wave not as a smooth curve, but as a series of numbers, voltage measurements taken at regular intervals. A digital camera does not capture a continuous image, but a grid of discrete pixels. An MRI machine does not measure a smooth spatial distribution, but a set of discrete data points in what physicists call K-space. To use Fourier's idea on real data, you need the discrete Fourier transform, the DFT. And the DFT has a problem. For n data points, computing the DFT requires n squared complex multiplications. That is the naive algorithm. It is simple, it is correct, and it is catastrophically slow. For 1,200 data points, you need about 1 million multiplications. That is manageable. For 1 million data points, which is what a few seconds of audio at CD quality gives you, you need 1 trillion multiplications. In 1965, the fastest computers in the world could not do that in a reasonable amount of time. And 1 million data points is nothing. A single MRI scan produces millions of data points. A single second of Wi-Fi traffic involves thousands of transforms on thousands of data points each. The Fourier transform was the right mathematical tool for everything, and it was computationally impossible to use at scale. The entire digital age was locked behind a wall of n squared. And here is where the story acquires its most bitter irony. The key to unlocking that wall, the algorithm that would reduce n squared to n log n, a speed up so enormous it would make the entire digital revolution possible, had already been discovered in 1805 by Carl Friedrich Gauss. 2 years before Fourier even presented his memoir to the Institut de France, Gauss, who is routinely called the greatest mathematician in history, was working on a completely different problem. He was trying to calculate the orbits of the asteroids Pallas and Juno, recently discovered objects in the solar system whose paths needed to be determined from a limited set of astronomical observations. To interpolate the orbital data, Gauss needed to compute trigonometric sums efficiently. And in his unpublished notes, in a manuscript titled Theoria Interpolationis Methodo Nova Tractata, he derived an algorithm that is essentially identical to what we now call the Fast Fourier Transform. He split the computation recursively, exploiting the symmetries of the trigonometric functions to reduce the total number of operations from n squared to something proportional to n log n. For 1 million data points, that is not a modest improvement. That is the difference between 1 trillion operations and 20 million operations, a speed-up factor of 50,000. Gauss never published it. He wrote it in Neo-Latin, the academic language of the day, tucked it into his personal papers, and moved on to other things. The manuscript was only published posthumously in his collected works in 1866, and even then, nobody recognized what it was. It sat in his work, Volume 3, in a dead language for nearly a century, the most consequential unpublished algorithm in human history, hidden in plain sight, because the man who discovered it did not think it was important enough to mention. I want you to feel the weight of that. Between 1805, when Gauss derived the fast algorithm, and 1965, when Cooley and Tukey independently rediscovered it, 160 years passed. 160 years, during which every scientist, every engineer, every physicist who needed to compute a Fourier transform was doing it the slow way. 160 years of wasted computation. And the solution was sitting in a dead mathematician's filing cabinet, written in a language nobody was reading. This is not the story of an idea ahead of its time. This is the story of an idea that arrived exactly on time and was immediately lost. Gauss had the algorithm. Fourier had the equation. If those two pieces had been connected in 1807, the trajectory of mathematics, physics, and engineering would have been altered by at least a century. But the pieces were not connected because Gauss did not publish, and Fourier was fighting Lagrange, and nobody was looking at the bigger picture. The bigger picture would not come into focus until the Cold War. In 1963, a meeting of President Kennedy's Science Advisory Committee was convened to discuss a problem that had nothing to do with mathematics in any obvious way. The problem was nuclear arms verification. The United States and the Soviet Union had signed the Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons tests in the atmosphere, in outer space, and underwater. But underground tests were still permitted, and the question was whether underground tests could be reliably detected and verified from outside the Soviet Union. Could you plant seismometers in the countries surrounding the USSR and use the seismic data to determine whether the Soviets were conducting secret underground nuclear detonations? You could, in principle. Nuclear explosions produce distinctive seismic signatures that differ from natural earthquakes. The physics of the detection was sound, but the mathematics was a nightmare. To distinguish a nuclear blast from an earthquake, you needed to analyze the frequency content of the seismic signals. You needed Fourier transforms, and the volume of data coming from an array of seismometers operating continuously was enormous. The DFT at n-squared operations per transform was too slow. The computation could not keep up with the data. At that meeting, a mathematician named John Tukey from Princeton University and Bell Labs described to the committee an approach for computing Fourier transforms much faster. Another participant, Richard Garwin, a physicist at IBM's Watson Research Center, immediately understood the implications. Garwin was working on nuclear verification. He had been thinking about exactly this problem. And he realized that if Tukey's fast method actually worked, it would change everything. But Garwin was also careful. The nuclear verification application was classified, or at least sensitive enough, that Garwin did not want the fast algorithm to be connected to it publicly. So when he went back to IBM, and enlisted James Cooley, a mathematician at the Watson Research Center, to implement Tukey's algorithm, he told Cooley something different. He told Cooley the algorithm was needed for determining the periodicities of spin orientations in a three-dimensional crystal of helium-3, a perfectly legitimate physics problem, and a complete cover story. Cooley figured out the real purpose eventually. But by then, he had implemented the algorithm, tested it, and confirmed that it worked. On an IBM 7094 computer, a size 2048 complex DFT that would have required over 4 million multiplications could now be computed in about 1.2 seconds. The speed up was not incremental. It was transformative. Cooley and Tukey published their paper in April of 1965 in Mathematics of Computation, Volume 19, pages 297 through 301. The title was An Algorithm for the Machine Calculation of Complex Fourier Series. It was 5 pages long. 5 pages that changed the world. And Tukey almost did not want to publish them. He felt the algorithm was a simple observation that was probably already known. He was right about the second part. Gauss had known it, but he was catastrophically wrong about the first. There was nothing simple about what this algorithm made possible. The Cooley-Tukey paper was eventually recognized as one of the most important scientific publications of the 20th century. In 2000, the journal Computing in Science and Engineering, published by the IEEE, named the Fast Fourier Transform one of the 10 most important algorithms of the 20th century. Gilbert Strang, the legendary mathematician at MIT, writing in American Scientist in 1994, called it the most important numerical algorithm of our lifetime. And the reason Strang was not exaggerating, the reason this 5-page paper from 1965 belongs in the same conversation as the discovery of antibiotics or the invention of the transistor, is that the FFT did not just make one application faster, it made everything faster. Every single application of Fourier's idea, in every field, in every industry, suddenly became computationally feasible. The dam broke, and the flood that came through reshaped the entire world. But before we follow that flood, I want to come back to the nuclear story for a moment, because the ending is not what you would expect. The sensors were planted. Darwin's seismic arrays were deployed in countries surrounding the Soviet Union. The FFT was used to process the data. And it worked. The system could locate underground nuclear explosions to within 15 kilometers of where they were occurring. The mathematics of an orphaned tailor's son from Auxerre, accelerated by an algorithm that Gauss had discovered and lost, and Cooley and Tukey had rediscovered, was now being used to monitor the most destructive weapons ever built. But there is a bitter footnote. By the time the Cooley-Tukey paper was published in 1965, it was already too late to stop the spread. Britain had tested its first nuclear weapon in 1952, France in 1960, China in 1964. The algorithm that could have enabled comprehensive nuclear verification arrived after the proliferation had already happened. The FFT almost stopped the nuclear arms race. Almost. If Gauss had published in 1805, if someone had recognized what he had, if the algorithm had been available decades earlier, the history of nuclear weapons might have been different. But Gauss did not publish, and the algorithm arrived too late. And now there are 9 nuclear-armed states and an estimated 12,500 nuclear warheads distributed across the planet. The pattern repeats. The right idea, discovered by the right person, at the right time, and then lost, suppressed, delayed, or ignored until the window of maximum impact has closed. Fourier's equation suppressed by Lagrange. Gauss's algorithm buried in unpublished Latin. The FFT arriving a decade after the nuclear club had already expanded. The story of Fourier analysis is not a story of inevitable progress. It is a story of near misses, of knowledge that existed before anyone was ready to use it, of opportunities that were fumbled and recoverable only at enormous cost. And now I need to show you what the FFT actually unleashed. Because the applications of Fourier's idea are not a list. They are not a catalogue of technologies that happen to use the same math. They are a revelation about what the world actually is, told one technology at a time. And it starts with the image on your screen. Every digital photograph you have ever seen, every image on every website, every picture on every phone, every frame of every video has been processed by a descendant of Fourier's 1807 equation. The JPEG compression standard, which is the backbone of digital imaging, works by applying a two-dimensional discrete cosine transform, a close cousin of the Fourier transform, to 8x8 pixel blocks of the image. The DCT was formalized by Nasir Ahmed, T. Natarajan, and K.R. Rao in a paper published in the IEEE Transactions on Computers in January of 1974. What it does is take an 8x8 block of pixel values, 64 numbers representing brightness and color, and convert them into 64 frequency coefficients. Instead of saying, this pixel is bright, this pixel is dark, this pixel is medium, the DCT says, this block has this much of the lowest frequency pattern, this much of the next frequency, this much of the next. And here is the insight that makes compression possible. For natural images, for photographs of the real world, almost all the energy, almost all the information that your eye actually cares about is concentrated in the low frequency coefficients. The high frequency coefficients, the ones that encode the finest, most rapid variations in brightness, are small, tiny, almost zero, and your visual system cannot really perceive them anyway. So you throw them away, you keep the big, low-frequency coefficients, and you discard the small, high-frequency ones. That is lossy compression. That is JPEG. And it typically achieves 10-to-1 compression with a quality loss that most people cannot see. Think about what that means. Every time you open an image on your phone, you are looking at the low-frequency Fourier reconstruction of reality. You are seeing the world through Fourier's eyes. The fine detail has been stripped away, the rapid variations deleted, and what remains is the smooth, low-frequency skeleton of the original scene. And you cannot tell the difference, because your brain, it turns out, also processes visual information in something very close to a frequency decomposition. Your visual cortex, the part of your brain that processes what you see, has neurons that respond to specific spatial frequencies. Your biology and Fourier's mathematics agree on what matters in an image. That is not a coincidence. That is a clue. But images are just the beginning. Every song you have ever streamed, every podcast you have ever downloaded, every phone call you have ever made on a digital network has been compressed using a variant of the Fourier transform. The MP3 codec, which has become the de facto shorthand for digital audio, works by running the audio signal through a modified discrete cosine transform, a close relative of the FFT, on overlapping windows of sound. Each window is broken into 32 frequency bands. A parallel 1024-point FFT runs a psychoacoustic model that determines which frequency bands your ear can actually hear, given the other sounds present. The frequencies your ear cannot perceive, either because they are masked by louder sounds at nearby frequencies or because they fall below your threshold of hearing, are discarded. The result is audio compressed to roughly 1/11 its original size, with quality that most listeners cannot distinguish from the uncompressed original. Your music is a frequency decomposition. Your images are a frequency decomposition, and the signal that carried them to your device is a frequency decomposition. Every Wi-Fi packet, every 4G phone call, every 5G data stream, every digital television broadcast, every digital radio signal uses a technology called orthogonal frequency division multiplexing, OFDM. The idea was first published by Robert W. Chang of Bell Labs in a 1966 paper in the Bell System Technical Journal. And what OFDM does is pure Fourier. The transmitter takes the data you want to send, maps it onto thousands of individual frequency channels, and then runs an inverse FFT to combine all those frequency channels into a single time domain signal that can be transmitted over a radio wave. The receiver does the opposite. It takes the incoming radio signal and runs a forward FFT to separate it back into the individual frequency channels and recover the data. Every Wi-Fi packet is an FFT. Every 5G frame is an FFT. Wi-Fi 6 uses 256 point FFTs at 20 MHz bandwidth. 5G new radio uses FFTs up to 4,096 points. Every time your phone connects to a cell tower, the handshake between your device and the tower involves dozens of FFTs exchanged in milliseconds. The wireless revolution, the thing that untethered the internet from cables and put it in your pocket, is a Fourier transform running billions of times per second across every radio on Earth. And it goes deeper than communication. It goes into your body. If you have ever had an MRI scan, or if someone you love has ever had one, then you have been inside a Fourier transform. Not metaphorically, literally. The MRI machine does not take a photograph of your body. It does not use light. It does not use X-rays. What it does is place your body in a powerful magnetic field, excite the hydrogen atoms in your tissues with radio frequency pulses, and then listen to the signals those atoms emit as they relax back to equilibrium. The signals it records are not images. They are raw frequency data, samples of the spatial Fourier transform of the hydrogen density in your body. The technical term for the data space that the MRI machine samples is K-space, and K-space is the Fourier transform of image space. To turn that raw frequency data into the image your doctor sees on the screen, the machine runs a 2-dimensional or 3-dimensional inverse FFT. That is it. That is the entire imaging principle. Your MRI is an inverse Fourier transform of your body's frequency response. Paul Lauterbur, who shared the 2003 Nobel Prize in Physiology or Medicine with Peter Mansfield for the development of MRI, published the foundational paper in Nature in 1973 under the title Image Formation by Induced Local Interactions. The title is deliberately vague because Lauterbur was worried the journal might reject a paper with nuclear magnetic resonance in the title, since the word nuclear frightened people. But the method he described is Fourier through and through. The gradient coils that the MRI machine uses to encode spatial information do so by varying the magnetic field in a way that maps spatial position to frequency. Position becomes frequency. The signal coming out of the receiver is a mix of all those frequencies, and the FFT separates them back into spatial locations. The image of your brain on the radiologist's screen is a Fourier decomposition of the magnetic resonance of the water molecules inside your skull. CT scans work on the same principle, approached from a different angle. A CT scanner shoots X-rays through your body at hundreds of different angles and records the attenuation, how much each ray is absorbed by the tissue it passes through. Each set of rays at a given angle is a line integral of the tissue density along that direction. The mathematical object formed by all these line integrals at all angles is called the radon transform of the tissue density. And there is a theorem, the Fourier slice theorem, sometimes called the central slice theorem, or the projection slice theorem, that says the one-dimensional Fourier transform of each angular projection is equal to a radial line through the two-dimensional Fourier transform of the tissue density, which means that if you take all the projections, Fourier transform each one, you fill up the two-dimensional frequency space of the tissue density, and an inverse FFT gives you the image. That is filtered back projection. That is how every CT scan in every hospital on Earth reconstructs the images that doctors use to find tumors, blood clots, fractures, and internal bleeding. Godfrey Hounsfield built the first commercial CT scanner in 1971. He and Alan Cormack shared the 1979 Nobel Prize. The mathematics they used was Fourier's. And here is where the applications stop being a list and start becoming something else, something closer to a statement about the nature of information itself. Shazam, the app that can identify a song from a few seconds of audio captured by your phone's microphone in a noisy room, works by computing a short-time Fourier transform of the audio snippet. The algorithm, published by Avery Lee-Chun Wang in a 2003 paper titled An Industrial Strength Audio Search Algorithm, at the ISMIR conference, takes 5 to 10 seconds of audio, runs an STFT to produce a spectrogram, a time-frequency map of where the energy is, identifies the peaks in that spectrogram, hashes them into a compact fingerprint, and matches the fingerprint against a database of millions of songs. The entire process takes milliseconds, and it works even when the audio is distorted by background noise, because the peaks in the Fourier transform are robust. The frequency content of a signal is more stable than the signal itself. Fourier's decomposition reveals what is invariant. In a sound, what survives even when the surface waveform is corrupted. That is why it works. Every voice assistant you have ever spoken to, Siri, Alexa, Google Assistant, every single one, starts by computing a short-time Fourier transform of your voice. The raw audio waveform from the microphone is windowed into short segments, typically 25 millisecond frames with 10 millisecond overlap, and each frame is run through an FFT to produce a spectrum. That spectrum is then converted into a MEL spectrogram, a frequency representation that approximates the response curve of the human ear. The neural network that recognizes your words never sees the raw waveform. It sees the Fourier transform of your voice. You speak in time. The machine hears in frequency. Noise-canceling headphones work by capturing ambient sound with a feed-forward microphone, computing a real-time FFT of that sound, typically 128 to 512 points, inverting the spectrum below roughly 1000 Hz, running an inverse FFT to produce the anti-noise signal, and playing it through the driver. The entire computation happens in microseconds. The silence you hear when you put on noise-canceling headphones is not the absence of sound. It is the precise negative Fourier transform of the sound around you. Radar and sonar both use Fourier analysis to extract target information from reflected signals. Pulse Doppler radar, the type used in military and civilian aviation, computes an FFT across a series of returned pulses to extract the Doppler shift of a moving target, which gives the target's radial velocity. Synthetic aperture radar, used in satellites and surveillance aircraft, synthesizes a virtual antenna thousands of meters long by combining radar returns taken at different positions along the flight path. And the image reconstruction is a two-dimensional Fourier inversion of the received echoes. Every weather radar image you have ever seen on a forecast is a Fourier transform of microwave reflections of raindrops. GPS receivers use FFT-based circular cross-correlation to acquire the pseudo-random codes transmitted by GPS satellites. The receiver compares its locally generated code to the satellite's code in the frequency domain. Because frequency domain correlation via FFT is enormously faster than time domain correlation, the position on your map is, at its computational root, a Fourier operation. And still, we have not reached the bottom, because the deepest application of Fourier's idea is not in engineering. It is not in medicine. It is not in communication or navigation or compression. The deepest application of Fourier's idea is in the laws of physics themselves. But before I go there, I need to take you back to 1952, to a laboratory in London, and to a photograph that changed the history of biology. Because that photograph is a Fourier transform, and the woman who took it was treated by the scientific establishment in a way that should sound familiar by now. On the 2nd of May, 1952, at King's College London, a physical chemist named Rosalind Franklin and her graduate student Raymond Gosling produced an X-ray diffraction image of the B form of DNA. It was labeled Photograph 51, and it is one of the most important images in the history of science. X-ray crystallography works on a principle that would have delighted Fourier. When X-rays pass through a crystalline substance, they scatter off the atoms in the crystal and produce a diffraction pattern on a photographic plate. That diffraction pattern is, mathematically, the Fourier transform of the electron density of the crystal. Not an analogy, not a metaphor. The diffraction pattern is literally, exactly, the squared magnitude of the Fourier transform of the atomic arrangement. The pattern of bright spots and dark bands encodes the spatial frequencies of the crystal structure. To determine the structure, you need to invert the Fourier transform to recover the spatial arrangement from the frequency data. This is called the phase problem, because the diffraction pattern gives you the magnitudes of the Fourier coefficients, but not their phases, and recovering the phases is extraordinarily difficult. Photograph 51 showed the distinctive X-shaped pattern that is the diffraction signature of a helix. Franklin, who was an expert crystallographer, understood what she was seeing. She was methodically working toward the structure of DNA through careful data analysis. But her colleague, Maurice Wilkins, showed the photograph to James Watson without her knowledge or consent. Watson, working with Francis Crick at Cambridge, used the information in photograph 51, together with their own model-building approach, to deduce the double helix structure of DNA. Their paper appeared in Nature in April of 1953. Franklin died of ovarian cancer on the 16th of April, 1958, at the age of 37, likely caused by the very X-ray radiation she had used to take the photographs. Watson, Crick, and Wilkins shared the 1962 Nobel Prize in Physiology or Medicine. The Nobel Prize cannot be awarded posthumously. Franklin received no credit in the Nobel citation. The structure of life, the double helix that encodes everything about your biology, was decoded using a Fourier transform. The photograph that revealed it was stolen from a woman who understood Fourier analysis better than the men who took credit for the discovery, and the radiation that produced the photograph killed her. Fourier's idea decoded the structure of DNA, and the structure of DNA killed the woman who took the picture. I am telling you this not just because it is important history, though it is, but because it demonstrates something about the Fourier transform that goes beyond technical utility. The Fourier transform does not just process data. It reveals hidden structure. It takes something that looks like noise, like a mess of scattered dots on a photographic plate, and shows you that underneath the apparent complexity, there is a clean, simple repeating pattern, a helix, a wave, a frequency. It strips away the surface and shows you what is really there. And that is exactly what it does in quantum mechanics, where the implications are not just disturbing. They are, I think, the most unsettling thing Fourier's equation has ever revealed about reality. And it is the thing that nobody taught you in school, not because it is controversial, not because it is new, but because the implication is so uncomfortable that the people who teach this would rather skip past it than explain what it actually means. Here is the fact. In quantum mechanics, the wave function that describes a particle's position and the wave function that describes that same particle's momentum are Fourier transforms of each other. I need to unpack that because it sounds technical, and it is anything but. The wave function is the mathematical object that contains everything knowable about a quantum system. If you know the wave function, You know the probability of finding the particle at any given position. You also know the probability of measuring it with any given momentum. But the position version of the wave function and the momentum version of the wave function are not independent descriptions. They are not two different pieces of information. They are the same information expressed in two different bases. And the mathematical relationship between them is the Fourier transform. Precisely, exactly the Fourier transform that Joseph Fourier developed to solve the heat equation in a metal bar in 1807. This was formalized through the de Broglie relation proposed by Louis de Broglie in his 1924 doctoral thesis, which states that the momentum of a particle is equal to Planck's reduced constant times its wave number. The wave number is a frequency, a spatial frequency. Momentum is frequency. Let that sit for a moment. In quantum mechanics, the most fundamental description of how much a particle is moving, its momentum, is a frequency, not a velocity, not a force, not an impulse, a frequency. And the relationship between the position description and the frequency description is the Fourier transform, which means Heisenberg's uncertainty principle, the one you were taught in school, the one that says you cannot simultaneously know a particle's position and momentum with arbitrary precision, is not some exotic quantum weirdness. It is not a limitation of measurement instruments. It is not about disturbing the particle by looking at it. It is the Fourier uncertainty theorem. I need to be clear about what that means. The Fourier uncertainty theorem is a purely mathematical result, known since the 19th century, that says a function and its Fourier transform cannot both be sharply localized. If a function is concentrated in a narrow region of space, its Fourier transform must be spread out over a wide range of frequencies, and vice versa. If you want a sharp frequency, you need a long, extended signal. If you want a sharp position, you need a broad frequency spectrum. This is not physics. This is mathematics. This is a property of the Fourier transform itself, and Heisenberg's uncertainty principle, the equation that sigma x times sigma p is greater than or equal to h bar over 2, where sigma x is the uncertainty in position and sigma p is the uncertainty in momentum, is exactly, precisely, the Fourier uncertainty theorem applied to quantum wave functions. Werner Heisenberg published the uncertainty relation in 1927. Earl Hayes Kennard gave the rigorous inequality in the same year. Hermann Weyl formalized it in 1928. But the mathematical truth behind it, the fact that a function and its Fourier transform trade off in sharpness, was already known. It was already implicit in everything Fourier had done a century earlier. The uncertainty principle is not a discovery about quantum mechanics. It is a discovery about the Fourier transform. It is a property of Fourier's equation, running at the most fundamental level of physical reality, enforcing a trade-off between complementary descriptions of the same system, position and momentum, time and energy, particle and wave. And this is the point where I want you to stop thinking about Fourier analysis as a tool and start thinking about it as a feature of the universe. Because here is the question that nobody in the physics education system wants to address directly. If the position description of reality and the frequency description of reality are related by a Fourier transform, and if neither description is more fundamental than the other, and if the Fourier transform is a lossless, invertible operation, meaning no information is created or destroyed when you switch between the two, then which one is real? Is the universe made of particles in positions, the way you experience it with your senses, or is the universe made of frequencies, the way the equations describe it at the deepest level? The answer from quantum mechanics, the honest answer, the answer that textbooks tend to rush past, is that neither description is privileged. They are dual. The position basis and the momentum basis are two equally valid representations of the same quantum state, related by a Fourier transform. The universe does not prefer one over the other. Your experience of solid objects in definite locations is a position basis description, but the momentum basis description, the frequency description, is equally real, equally complete, equally valid. You could, in principle, describe the entire universe in the frequency domain and never mention positions at all. You would lose nothing. Every fact about reality would still be there. It would just look completely different. And the reason this should unsettle you is that the frequency description looks nothing like the world you think you live in. In the frequency domain, there are no objects, there are no locations, there are no boundaries between things. There are just frequencies, amplitudes, and phase relationships. A rock in the frequency domain is a collection of standing wave patterns. A human body is an extraordinarily complex superposition of quantum frequency modes. The distinction between you and the air around you, which seems so obvious in position space, is not obvious in frequency space. In frequency space, you and the air are different patterns in the same field, distinguished not by location, but by spectral content. This is not mysticism. This is not New Age speculation. This is the standard mathematical framework of quantum mechanics, taken seriously, followed to its logical conclusion. The Fourier transform is not just a computational tool that happens to be useful. It is the bridge between two equally valid descriptions of reality. And the fact that it works, the fact that every physical signal satisfies the conditions for Fourier decomposition, is telling us something about what the universe is. Fourier did not know this. He was solving a heat problem. He was trying to figure out how temperature distributes itself along a metal bar. He had no conception of quantum mechanics, no idea that his equation would describe the relationship between position and momentum, no way of knowing that the mathematical structure he was building would turn out to be the operating system of physical reality. But the mathematics did not care what he intended. The mathematics was true, regardless of whether he understood its implications, and the implications have only grown deeper with every decade since his death. Let me give you one more example, the most dramatic one, before I pull this all together. On the 14th of September, 2015, at 5:51 in the morning Eastern Daylight Time, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time in human history. The signal, designated GW150914, came from two black holes spiraling into each other 1.3 billion light-years away. The black holes had masses of 36 and 29 solar masses respectively. They merged to form a single black hole of 62 solar masses. The missing 3 solar masses, equivalent to the energy output of the Sun over its entire 10 billion year lifetime, multiplied by several billion, was radiated as gravitational waves in less than 1 second. The signal that LIGO detected was unimaginably small. The gravitational wave stretched and compressed the 4-kilometer-long arms of the detector by a distance of approximately 1/1000th the diameter of a proton. To detect that, LIGO had to distinguish the gravitational wave signal from an enormous background of noise. Seismic vibrations, thermal fluctuations, quantum noise in the laser, even passing trucks on a nearby highway could all produce disturbances larger than the signal. And the way LIGO did it was matched filtering. In the frequency domain, every segment of LIGO's strain data is Fourier transformed, multiplied in the frequency domain by template waveforms that represent what a gravitational wave from a merging black hole binary should look like. weighted by the inverse of the noise power spectral density, a technique called Wiener filtering, and then inverse Fourier transform to produce a signal-to-noise ratio as a function of time. The Pi-CBC and GSTLAL pipelines that analyze LIGO data both work this way. Without the FFT, without the ability to rapidly move between the time domain and the frequency domain, real-time gravitational wave astronomy is computationally impossible. The signal is there, in the data, but it is invisible in the time domain. It only becomes visible when you look at it through Fourier's equation. The first detection of gravitational waves, the direct confirmation of Einstein's 1915 prediction that space-time itself can ripple, was made possible by a mathematical tool developed by a tailor's orphan in Grenoble to describe how heat moves through a metal bar. And I think at this point, you can start to see something that goes beyond utility, beyond application, beyond coincidence. Fourier's equation does not just happen to work in all these different contexts. It works because it is describing something real about the structure of information, about the way the universe organizes itself, about the relationship between signals and their frequency content. That is not just a mathematical convenience, but a physical fact. Consider what we have catalogued so far. Fourier analysis is in your images, in your music, in your wireless communication, in your medical imaging, in the way your voice assistant hears you, in the detection of gravitational waves, in the structure of DNA, in the uncertainty principle of quantum mechanics, in the noise-cancelling headphones on your head, in the radar that tracks your weather, in the GPS that knows where you are, in the seismographs that detect earthquakes, in the nuclear verification systems that monitor arms treaties. It is in every digital oscilloscope, every spectrum analyzer, every telephone system built since the 1980s. It is in the compression algorithm that encodes every video on Netflix and YouTube and every stream on Spotify. It is in the image processing that runs on the processors of every OLED and LCD display. It is in financial time series analysis and protein crystallography and dark matter detection experiments and functional MRI studies of the brain. I want to put a number on this so it becomes concrete. As of 2025, IoT Analytics estimates there are approximately 21 billion connected devices on Earth. Smartphones alone account for over 7 billion subscriptions. Every one of those devices that has a radio, which means every Wi-Fi enabled device, every cellular phone, every Bluetooth speaker, every connected thermostat, runs FFTs continuously. A 5G radio performs an FFT approximately every 71 microseconds per active OFDM symbol. There are billions of active radios on the planet at any given moment. A defensible order of magnitude estimate for the total number of FFTs running globally across all cellular, Wi-Fi, and Bluetooth radios, not counting audio and video codecs, not counting medical imaging, not counting scientific computing, is tens of trillions per second. Tens of trillions per second. An equation written by an orphan in 1807. That is not a tool being applied. That is a fundamental operation of the technological substrate of human civilization. If the Fourier transform stopped working tomorrow, if some law of mathematics changed and the decomposition of functions into frequency components became invalid, every phone would go silent, every screen would go dark, every Wi-Fi network would collapse, every MRI machine would produce noise, every GPS would lose position, every digital broadcast would become static, and every gravitational wave detector would go blind. Not because these technologies chose to use Fourier analysis, because they have no choice, because the problems they solve have no other solution, because the Fourier transform is the only bridge between the time domain and the frequency domain, and every one of these technologies needs to cross that bridge to function. There is no substitute. There is no alternative algorithm that does what the Fourier transform does. There are variations, there are related transforms, there are wavelets and Laplace transforms and Z transforms that handle specific cases differently. But the core operation, the decomposition of a signal into its frequency components and the reconstruction of a signal from those components, is Fourier. It has been Fourier since 1807, and it will be Fourier for as long as the mathematical structure of the universe remains what it is. I want to come back now to the question I raised at the beginning, because I think the evidence forces it. Is the universe made of things, or is it made of frequencies? Here is what we know. Every physical signal that has ever been measured obeys the Fourier decomposition. Every vibration, every electromagnetic wave, every quantum state, every gravitational ripple. The Dirichlet conditions that guarantee convergence of the Fourier series are satisfied by every physical signal, without exception. No physical process has ever produced a function that violates them. The pathological functions that break Fourier's theorem, the ones that Dubois-Raymond constructed in 1873, are mathematical curiosities that exist only in the abstract. The physical universe does not produce them. As if the universe were designed, or had evolved, or simply is, in a way that makes Fourier analysis not just applicable, but inevitable. In quantum mechanics, the relationship is even deeper. Position and momentum are not just related by a Fourier transform, they are conjugate variables, meaning that the Fourier relationship between them is built into the structure of quantum theory at the axiomatic level. You cannot have quantum mechanics without the Fourier transform. Remove it, and the entire framework collapses. The uncertainty principle disappears. The position-momentum duality disappears. The wave-particle duality disappears. The Fourier transform is not a tool that quantum mechanics uses. It is a load-bearing structural element of the theory itself. And this extends beyond position and momentum. Time and energy are also Fourier conjugate. The time-energy uncertainty relation, delta E times delta T greater than or equal to h bar over 2, is the same Fourier uncertainty theorem in a different pair of conjugate variables. Angular position and angular momentum are Fourier conjugate. Every pair of complementary observables in quantum mechanics is related by a Fourier transform. The entire framework of quantum mechanics, the most precise and experimentally verified theory in the history of science, is built on the mathematical structure that Joseph Fourier discovered while trying to understand how heat flows through a bar of metal. The Nobel laureate physicist Richard Feynman once said, describing the double-slit experiment, that it contains the only mystery of quantum mechanics. But the mystery of the double-slit experiment is the mystery of wave interference, which is the mystery of superposition, which is the mystery of the Fourier decomposition. When a particle passes through two slits and produces an interference pattern on the far screen, it is because the quantum wave function, which is a complex-valued function of position, contains multiple frequency components, and those frequency components interfere constructively and destructively, depending on the path difference. The interference pattern is a Fourier phenomenon. The strangeness of quantum mechanics is, at its mathematical core, the strangeness of the Fourier transform taken seriously as a description of physical reality. And I still do not know how to think about that. I have read the papers. I have followed the mathematics. I have traced the line from Fourier's heat equation to the Heisenberg uncertainty principle, to the quantum field theories that describe every particle in the Standard Model. And at the end of that line is a conclusion that I can state precisely but cannot fully absorb. The universe has a dual description. One description is in position space. The the space of objects and locations and distances, the space your senses evolved to perceive. The other description is in frequency space, the space of oscillations and wave numbers and spectral densities, the space that every instrument and every equation accesses through the Fourier transform. The two descriptions are mathematically equivalent. Neither is more real than the other. The Fourier transform converts between them without any loss of information. And the description you experience, the world of solid objects and distinct boundaries and things in places, is just one basis, just one way of reading the same quantum state. The frequency description is equally valid, and in the frequency description, there are no objects, there are no things, there are only patterns of oscillation in fields, some localized, some extended, all coexisting in a single, unified frequency spectrum that includes everything from the cosmic microwave background to the gamma rays of nuclear decay, to the sodium and potassium ion oscillations firing in your neurons right now as you process this sentence. That is what Fourier's equation reveals about reality when you follow it all the way down. Not that reality has a frequency description. That reality is a frequency description. The position space version, the world of things and places, is a Fourier transform of something deeper, something that does not look like the world you know, something that looks like a spectrum. Terence Tao, the Fields Medal laureate, writing in the Princeton Companion to Mathematics in 2008, described the Fourier transform as a systematic way to decompose generic functions into a superposition of symmetric functions. What he was describing, in mathematically precise language, is exactly what the universe does. It decomposes, it superposes, it builds complex structures from simple oscillations and simple oscillations from complex structures. The Fourier transform is not a lens through which we choose to view reality. It is the operation reality uses to build itself. And now I want to bring this back to Fourier, to the man himself, because the story is not complete without the ending, and the ending is not what you expect. Fourier died on the 16th of May, 1830, at the age of 62, from a heart condition that had been worsening for decades. He spent his last years as the most powerful administrator in French science, the permanent secretary of the Académie des Sciences, editing the journal, managing the publications, evaluating the submissions. He had finally published his masterwork, The Théorie analytique de la chaleur, in 1822. He had been elected to the Académie Française. He had been elected to the Académie de Médecine. The orphan from Auxerre had achieved a level of recognition that would have been unimaginable to the boy scraping candle wax off dormitory tables. But the recognition was incomplete, and the incompleteness has a specific shape that tells you something about how the scientific establishment handles ideas that are too large to categorize. Fourier was recognized for solving the heat equation. He was recognized for developing a useful mathematical technique. He was recognized as a skilled administrator and a competent physicist. What he was not recognized for, what nobody in 1830 could have recognized him for, was the true nature of what he had discovered. He thought he had found a method for solving a particular class of differential equations. He had actually found the operating system of physical reality. But nobody could see that in 1830, because the physics that would reveal it, quantum mechanics, electromagnetism, information theory, digital signal processing, would not exist for another century. And there is something else Fourier did, something that nobody in his own time understood, and that has only recently been recognized as prescient. In 1824 and 1827, Fourier published 2 papers on the temperature of the Earth. The first, Remarques générales sur la température du globe terrestre et des espaces planétaires, appeared in the Annales de chimie et de physique, volume 27, in 1824. The expanded version, Mémoires sur les températures du globe terrestre et des espaces planétaires, appeared in the Memoirs de l'Académie royale des sciences, volume 7, in 1827. In these papers, Fourier posed a question that nobody else was asking. The Earth is in thermal equilibrium, roughly. It receives energy from the sun and radiates energy into space. But simple calculations show that the Earth's surface temperature was higher than it should be if the planet were just a bare rock radiating freely into the vacuum. Something was trapping heat. Something in the atmosphere was allowing sunlight to pass through on the way in, but blocking some of the infrared radiation on the way out. Fourier had identified the greenhouse effect, not in detail, not with the precision of John Tyndall, who in 1859 would identify carbon dioxide and water vapor as the key absorbing gases, and not with the quantitative rigor of Svante Arrhenius, who in 1896 would calculate the warming expected from a doubling of atmospheric carbon dioxide. But Fourier was the first person to pose the question in a physically coherent way, to recognize that the atmosphere must be selectively transparent, and to argue that this selective transparency was responsible for the habitable temperature of the planet. Think about the range of what this one man discovered. The mathematics of frequency decomposition, the physics of heat conduction, the first argument for atmospheric heat trapping. One human being in one career, disrupted by revolution, war, exile, political arrest, and institutional suppression, produced foundational work in 3 separate fields, any one of which would justify a permanent place in the history of science. And we named a unit of measurement after Kelvin, a crater after Lagrange, a constant after Planck. But the name Fourier is known to most people only as a prefix on a mathematical technique they were forced to learn for an exam and immediately forgot. There is a revealing asymmetry in how scientific culture treats its heroes. The physicists who built on Fourier's work are household names. Maxwell used Fourier analysis in his equations of electromagnetism. Heisenberg's uncertainty principle is Fourier's uncertainty theorem. Lauterber's MRI is an inverse Fourier transform. Einstein's photoelectric effect is a statement about the frequency modes of light. Every one of these scientists is famous. Fourier, whose mathematical structure they all depend on, is a footnote, not because his contribution was smaller, because his contribution was too big. It spread so far, infected so many fields, became so fundamental, that it stopped being associated with a person and started being treated as a fact of nature, which, in fairness, it is. But facts of nature were discovered by people, and this one was discovered by an orphan who was told he was the wrong kind of person for his work to count. The man who wrote the equation governing heat flow in solids was also the first person to recognize that heat flow in the atmosphere determines whether life is possible on Earth. And the irony is that 2 centuries later, the greenhouse effect he identified, amplified by industrial emissions of the very gases Tyndall and Arrhenius would later study, is the defining environmental crisis of human civilization. Fourier discovered the mechanism by which we are warming our own planet. And we have spent 200 years refusing to fully reckon with the implications of his observation, just as Lagrange refused to reckon with the implications of his mathematics. The pattern is always the same. Someone discovers something true. The establishment resists. The implications are ignored or downplayed. And by the time the truth is accepted, the damage is already done. But I want to push deeper on the physics, because I promised you at the beginning that this story leads somewhere that changes how you experience ordinary life. And I have not gotten there yet. Think about what it means for position and momentum to be Fourier conjugate. Think about what it means for the uncertainty principle to be a theorem about the Fourier transform rather than a statement about measurement disturbance. It means that precision in one domain costs you precision in the other, not because your instruments are bad, not because the particle is being bumped, because the information itself does not exist simultaneously in both descriptions at full resolution. A quantum state that is sharply localized in position, a particle that you know is right here, must be maximally delocalized in momentum, meaning you know nothing about how fast it is going or in what direction. And a quantum state that has a precise momentum, a particle moving at exactly this speed in exactly this direction, must be spread out over all of space. It is not anywhere in particular. It is everywhere. This is not a limitation of our knowledge. This is a property of the Fourier transform. A narrow pulse in time has a broad frequency spectrum. A pure tone, a single frequency, extends forever in time. You cannot have a signal that is both brief and narrowband. The information forbids it. And quantum mechanics says that particles are signals. Their wave functions are the signals, and the uncertainty principle is the bandwidth theorem of those signals. Which means the solid, localized, well-defined objects you think you see around you, the table, the wall, your own hand, are not as well defined as they appear. Every atom in the table has a wave function. That wave function has a position distribution and a momentum distribution, related by the Fourier transform. The position distribution is sharply peaked, yes, which is why the table looks solid, but the momentum distribution is correspondingly broad. The atoms in the table are, in the frequency domain, smeared across a wide range of momentum states. They are vibrating, oscillating, fluctuating in ways that the position space description smooths over. The solidity you feel when you put your hand on a table is a position space illusion, not in the sense that it is fake, in the sense that it is one basis of a deeper, richer, dual description, and the other basis looks nothing like a table. Your hand is not a thing. It is a pattern, a spectral pattern in a quantum field, temporarily coherent, briefly stable, held together by electromagnetic forces that are themselves frequency phenomena. The electrons in the atoms in your skin are not particles in orbits. They are standing wave patterns in the electron field, with specific energy levels that correspond to specific frequencies. The photons that bounce off your hand and enter your eye are frequency modes of the electromagnetic field. The neural signals that your brain uses to construct the experience of having a hand are electrochemical oscillations, frequency coded by the ion channels in your neurons. At every level, from the quantum fields to the biological signals, you are a frequency phenomenon, a Fourier decomposition in a universe that is, at its most fundamental level, a spectrum. I want to stop here and be careful, because this is the line where legitimate physics bleeds into metaphysical speculation, and I want to stay on the right side of it. I am not saying the universe is made of vibrations in some New Age sense. I am not invoking consciousness or observer effects or mystical frequencies. I am describing the standard mathematical framework of quantum field theory, in which the fundamental objects are fields, not particles, and particles are excitations of those fields, which is to say, they are frequency modes. An electron is a quantized excitation of the electron field at a specific energy, which means a specific frequency. A photon is a quantized excitation of the electromagnetic field at a specific frequency. The entire standard model of particle physics, every quark, every lepton, every boson, is a catalogue of frequency modes of quantum fields. That is not speculation. That is the working framework of modern physics. and the mathematical backbone of that framework, the operation that connects the field description to the particle description, the operation that defines the relationship between conjugate observables, the operation that enforces the uncertainty principle, is the Fourier transform. Now think about what this means for the concept of identity, for the concept of you as a separate, bounded, localized entity. In position space, you are a body. You have edges. Your skin defines a boundary between you and not you. You are here, and the rest of the universe is there. This seems obvious. It seems undeniable. In frequency space, that boundary dissolves. In frequency space, you are a pattern of excitations in quantum fields that extends, technically, over all of space, with an amplitude that is large here and small there, but never exactly zero anywhere. The fields that constitute you, the electron field, the quark field, the electromagnetic field, are not your fields. They are the universe's fields. You are a local concentration of activity in fields that are everywhere, and not in a net that spans all of space. In the frequency basis, the question, where do you end and the universe begins, does not have a clean answer. Because in the frequency basis, you and the universe are different spectral patterns in the same fields. This is the implication that Fourier's equation leads to when you follow it all the way down. Not just that reality has a frequency description, not just that the frequency description is equally valid, but that in the frequency description, the boundaries you take for granted, the boundaries between objects, between people, between self and world, are not fundamental. They are features of the position basis. In the frequency basis, everything is connected, not in a vague spiritual sense, in a mathematically precise Fourier transform related sense. And Fourier had no idea. He was trying to figure out how a hot piece of metal cools down. He was sitting in a prefectural office in Grenoble, managing road construction and swamp drainage for Napoleon. And in his spare hours, he wrote down an equation that describes the deepest structural feature of physical reality. An equation that, 2 centuries later, would run inside every device on the planet, while simultaneously describing the relationship between the two faces of quantum mechanics. I keep coming back to that image of the boy in Auxerre, scraping candle wax from garbage, melting it into stubs, studying mathematics by stolen light in an empty classroom. He had no money, no parents, no noble blood, no right to a future. The system told him he was the wrong kind of person for his work to count. And the equation he wrote, the one the system tried to suppress, the one Lagrange refused to accept, the one the committee would not publish for 15 years, that equation became the single most executed mathematical operation in human history, running tens of trillions of times per second, in every country, on every continent, in the ocean on submarine sonar arrays, in space on satellite transponders, in hospitals saving lives, in laboratories detecting the ripples of colliding black holes. There is a specific cruelty to the fact that Fourier never knew. He died thinking he had made a contribution to the theory of heat. He died thinking his mathematical technique was useful for a class of differential equations. He died not knowing that his equation would run every screen and signal on Earth, not knowing that it would decode the structure of DNA, not knowing that it would detect gravitational waves, not knowing that it was the mathematical backbone of quantum mechanics, not knowing that it described the dual nature of physical reality itself. He died on a staircase, wrapped in blankets, with a dead young man's stolen manuscript somewhere in his house, never to be found. And I want to stay with that image for a moment, because I think it tells you something about the nature of discovery that the popular narrative of science always gets wrong. The popular narrative says science is a march of progress. Genius has an idea. The idea is tested. The idea is confirmed. The idea changes the world. Clean, linear, inevitable. That is not what happened with Fourier. What happened with Fourier is that a traumatized orphan shaped by poverty and violence, obsessed with a physical phenomenon that was also a psychological one, heat, warmth, the thing he could never get enough of after his years in the Egyptian desert, wrote an equation that the most powerful people in his field declared wrong, and that the most powerful institution in his country suppressed for a decade and a half. He won the prize, but not the recognition. He got the title, but not the publication. He was technically wrong in the way that was politically convenient to attack, and fundamentally right in the way that nobody alive could yet appreciate. And then he died, and took Galois' manuscript with him. That is the real story of how the most important equation in modern technology entered the world. Not with a triumphant announcement, not with instant recognition, not with a Nobel Prize or a standing ovation. With suppression, delay, partial credit, accidental destruction, and a fall down a flight of stairs. And if you are angry about that, good, you should be, because the pattern has not stopped. The Fourier Transform is the most ubiquitous mathematical operation on the planet, and it is taught, when it is taught at all, as a technique, a method, a section in a textbook between Laplace transforms and partial differential equations. Students are shown how to compute the coefficients. They are tested on convergence conditions. They are given engineering problems to solve. And then they move on. Nobody tells them that the equation they just learned is the reason their phone works, the reason their MRI works, the reason the uncertainty principle exists. Nobody tells them that position and momentum are Fourier pairs. Nobody tells them that the equation describes the dual nature of reality. Nobody tells them the human story, the orphan, the guillotine, the desert, the ambush, the suppression, the staircase, the lost manuscript. The safe version. That is what they get. The safe, boring, technical version of the most extraordinary mathematical discovery in human history. And the reason they get the safe version is the same reason Lagrange suppressed the original paper, because the implications are too large, because following Fourier's equation to its logical conclusion forces you to confront a description of reality that does not look like the world you live in, a description in which objects are illusions, boundaries are approximations, and you are a temporary frequency pattern in a universal spectrum. Nobody wants to teach that in an engineering class, so they teach you how to compute the coefficients, and they move on. I spent a long time reading about Fourier before writing this, and the thing I keep coming back to is a sentence from his Théorie analytique de la chaleur that is usually quoted out of context, as a philosophical aside, but that I think is the most important sentence he ever wrote. Mathematics compares the most diverse phenomena and discovers the secret analogies which unite them. He wrote that in 1822. He was talking about heat, but he was also, without knowing it, describing his own equation's future. The Fourier transform connects JPEG compression and quantum mechanics. It connects MRI imaging and gravitational wave detection. It connects DNA crystallography and noise-cancelling headphones. It connects the greenhouse effect and submarine sonar. The most diverse phenomena, the secret analogies which unite them. Fourier saw the pattern. He could not see how far it went, because the physics that would reveal the full depth, quantum field theory, would not exist for another century. But he saw the pattern. He saw that the same mathematical structure appears in wildly different physical contexts. He saw that the universe repeats itself, uses the same tricks at different scales. solves different problems with the same equation. And he wrote it down in a book that was suppressed, in a career that was interrupted by revolution and war and political exile, in a life that ended on a staircase. And now his equation runs the world. Every second, every device, every signal, every screen, every scan, every call, every search, every stream, every measurement of every ripple in spacetime. Not because we chose it, because reality chose it first. I want to address something directly, because I think there is a misconception about Fourier analysis that has been quietly doing damage for decades, and correcting it is necessary for what comes next. If you took a college-level math or engineering course, you were probably taught that the Fourier transform is a mathematical tool, a technique for solving differential equations, a method used in signal processing, something that engineers need and pure mathematicians tolerate. That framing is not just incomplete, it is backwards. The Fourier transform is not a technique that humans invented to process signals. It is a structure that the universe uses to organize reality, and humans eventually noticed it, after 200 years of using it without understanding what it was. Think about the ordering of events. Fourier derived his equation in 1807 to solve a physics problem, the heat equation. For the next century and a half, the Fourier transform was applied to progressively more physics problems, not because engineers went looking for applications, but because every new branch of physics they explored turned out to have Fourier structure already baked into it. Electromagnetism, Fourier acoustics, Fourier optics, Fourier quantum mechanics, Fourier signal processing, Fourier information theory, Fourier. Every time physicists opened a new door, the Fourier transform was already inside the room, waiting. This is not what a tool looks like. A tool is something you bring to a problem. A hammer does not appear spontaneously inside every house you try to build. But the Fourier transform does appear spontaneously inside every physical system you try to describe. That pattern is not about us. It is about the universe. It is telling us that the frequency decomposition is not a human invention imposed on physics. It is a physical fact that physics imposes on us. And here is where the brain becomes part of the story, because the Fourier transform does not just describe external physical systems. It describes the internal system you use to perceive them. Your auditory system performs something very close to a Fourier transform on every sound you hear. The cochlea in your inner ear is a spiral-shaped organ lined with approximately 15,000 hair cells. Each hair cell is tuned to respond to a specific frequency of sound. High-frequency sounds activate hair cells near the base of the cochlea. Low-frequency sounds activate hair cells near the apex. When a complex sound enters your ear, a sound containing many frequencies simultaneously, the cochlea separates that sound into its frequency components and sends each component to the brain as a separate neural signal. Your ear is, in a very real sense, a biological Fourier analyzer. It takes a time-domain signal, the pressure wave hitting your eardrum, and converts it into a frequency domain representation, the pattern of neural activation along the cochlea. Your visual system does something analogous. The neurons in your primary visual cortex, area V1, include cells that respond to specific spatial frequencies, specific patterns of light and dark, at specific scales. Some cells respond to fine, high-frequency texture. Others respond to broad, low-frequency gradients. The visual cortex decomposes the image on your retina into spatial frequency components, much like a two-dimensional Fourier transform. This is not a metaphor. Neuroscientists have measured the spatial frequency tuning curves of individual cortical neurons. Your brain processes vision in something that is functionally, measurably close to a Fourier decomposition, which means the Fourier transform is not just in the physics outside your body and the technology in your hand. It is in the biology of your perception. Your ears hear in Fourier, your eyes see in Fourier. The neural patterns that encode your sensory experience are frequency representations. The universe presents information in the frequency domain. Your senses receive information in the frequency domain. And the technology between the two, the microphones and speakers and screens and radios, all operate in the frequency domain. The entire chain, from the physics of the signal to the engineering of the transmission to the biology of the perception, is Fourier at every link, without exception. And none of this was designed. Nobody planned it. Nobody coordinated the physics with the biology, with the engineering. The Fourier structure is there because it is a feature of information itself, a feature that the universe exhibits, that evolution exploited, and that technology discovered independently. There is also a piece of the FFT story I have not told you yet, because it involves one of the most haunting near misses in the history of computation. In 1942, 23 years before Cooley and Tukey's paper, two researchers named Gordon Danielson and Cornelius Lanczos published a paper in the Journal of the Franklin Institute, volume 233, describing a recursive doubling trick for computing Fourier transforms. Danielson was Lanczos' student. Their paper, Some Improvements in Practical Fourier Analysis and Their Application to X-ray Scattering from Liquids, described an approach that is mathematically equivalent to the radix 2FFT. They even reported the results of a manual computation, done by hand, of a 64-point DFT. It took 140 minutes, by hand, with pencil and paper. They had the algorithm. In 1942, if they had been working with a computer instead of pencil and paper, if the electronic computer had arrived just a few years earlier, the FFT revolution would have started 2 decades sooner. Digital communications, medical imaging, audio compression, all of it could have come 20 years earlier. But Danielson and Lanczos were computing by hand, and their paper was read as a practical improvement to manual calculation, not as a theoretical breakthrough in algorithmic complexity. It was cited, it was known, and its full significance was not recognized. Gauss in 1805, Danielson and Lanczos in 1942, Cooley and Tukey in 1965. The same algorithm, discovered 3 times across 160 years, and only on the 3rd discovery did anyone realize what it meant. The FFT is the most important algorithm in modern technology, and the human race had to discover it 3 times before it stuck. The pattern holds: the right idea, the right time, and the wrong response, over and over, as if the universe were trying to hand us the key, and we kept dropping it. Now I want to take you back inside the technology for a moment, because I think the scale of what I am describing has not fully landed, and I need it to land before the ending. You are watching this video, or you are listening to it. Either way, a Fourier transform is involved in getting my voice to your ears right now. The audio was recorded by a microphone that converts sound pressure into an electrical signal. That signal was digitized at a sampling rate of 44,100 samples per second or higher. The raw audio was then encoded using a codec, likely AAAC or Opus, both of which use a modified discrete cosine transform at their core. The MDCT takes overlapping windows of the audio, 1024 or 2048 samples each, transforms them into the frequency domain, applies a psychoacoustic model to determine which frequency components your ear actually needs, discards the rest, and encodes the survivors. The compressed bit stream was then uploaded to a server and stored. When you clicked play, the compressed data was transmitted to your device. If you are on Wi-Fi, that transmission used OFDM, which means the data was modulated onto hundreds of orthogonal subcarriers using an inverse FFT at the transmitter and recovered using a forward FFT at your device's radio. If you are on cellular, the same OFDM process occurred between your phone and the cell tower. Once the compressed data reached your device's processor, it was decoded by inverting the MDCT, reconstructing the time domain audio signal, and sending it to the digital to analog converter that drives your speakers or headphones. Count the Fourier transforms in that chain. The psychoacoustic model in the encoder runs an FFT. The MDCT in the encoder is a Fourier-related transform. The OFDM transmitter runs an inverse FFT. The OFDM receiver runs a forward FFT. The MDCT decoder inverts the frequency domain representation. If you are wearing noise-cancelling headphones, add two more, the forward FFT of the ambient noise and the inverse FFT of the anti-noise signal. That is at least 6 Fourier transforms in the chain between my voice and your ear. And if you are watching video, the visual stream adds its own chain of DCT operations, one for every 8x8 block of every frame, running at 24 to 60 frames per second. Right now, at this moment, the system that is delivering this information to you is executing thousands of Fourier transforms per second. And that is one video stream on one device. Multiply by the number of active video and audio streams on the planet at any given moment. Multiply by the number of Wi-Fi and cellular connections active at any given moment. Multiply by the number of MRI machines and CT scanners running in hospitals. Multiply by the number of radar installations and sonar arrays and GPS receivers and spectrum analyzers and seismographs and gravitational wave detectors. The total number of Fourier transforms being computed on Earth right now is a number so large it resists comprehension. Tens of trillions per second is a conservative lower bound. The actual number may be orders of magnitude higher, and every single one of those operations traces its lineage back to a memoir read by a provincial prefect before the Institut de France on the 21st of December, 1807. A memoir that was rejected, a memoir that was suppressed, a memoir that contained a claim so bold that the greatest mathematician in Europe refused to believe it. I want to talk about what Fourier's equation does that nothing else can, because understanding this is the key to understanding why it is not replaceable and why it appears everywhere. The Fourier transform converts between two representations of information. One representation describes how a quantity varies over time or space, the time domain or space domain. The other representation describes how much of each frequency is present, the frequency domain. The relationship is bidirectional and lossless. No information is created or destroyed. The time domain representation and the frequency domain representation contain exactly the same information, organized differently. This is enormously useful for engineering, because many operations that are difficult in the time domain become trivial in the frequency domain, and vice versa. Filtering, for example. If you want to remove high-frequency noise from a signal, you could try to design a time domain filter, which involves convolution, a computationally expensive operation. Or you could Fourier transform the signal, set the high-frequency coefficients to 0, and inverse transform back. In the frequency domain, filtering is just multiplication, and multiplication is fast. Convolution in the time domain is multiplication in the frequency domain. That is the convolution theorem. one of the most important results in signal processing, and it is a direct consequence of the properties of the Fourier transform. It is the reason that matched filtering at LIGO works in the frequency domain. It is the reason that GPS acquisition is done in the frequency domain. It is the reason that image processing, audio processing, and telecommunications all route through the FFT. Because operations that would be computationally prohibitive in the time domain become simple multiplications in the frequency domain. But there is something deeper happening. The Fourier transform does not just make computation faster. It reveals structure that is invisible in the time domain. A sound that sounds like noise, a random hiss, may contain a hidden periodic signal that is perfectly visible in the frequency domain as a spike at a particular frequency. LIGO's gravitational wave detection is exactly this scenario. The time domain strain data looks like noise. The signal is buried. But in the frequency domain, after matched filtering, the signal emerges clearly. The Fourier transform does not just process information. It sees through it. It sees through the surface complexity to the underlying structure. It is, in a very real sense, a way of seeing what is really there. And that is why it works in quantum mechanics. Because quantum mechanics is, at its mathematical core, a theory about what is really there, underneath the appearances. The position space wave function, the one that tells you where a particle is the appearance. The momentum space wave function, the one that tells you how the particle is moving, is the other appearance. Neither is more real. Neither is more fundamental. The Fourier transform connects them, because the Fourier transform is the operation that relates dual descriptions of the same underlying reality. In signal processing, that underlying reality is a signal. In quantum mechanics, that underlying reality is a quantum state. In both cases, the Fourier transform is the translator between two faces of the same thing. I want to make one more connection before the end, because I think it is the one that ties everything together, and it is the one that was buried the deepest, the bandwidth theorem. In telecommunications, there is a fundamental trade-off between the bandwidth of a signal and the duration over which it is defined. A signal that is brief in time must have a wide bandwidth. A signal that is narrowband must be long in duration. This is not a limitation of technology. This is a mathematical consequence of the Fourier transform. And the formula that expresses this trade-off is identical, mathematically identical, to Heisenberg's uncertainty principle. The time bandwidth product, delta t times delta f, is always greater than or equal to 1 over 4 pi for Gaussian signals, which is the same constant relationship as delta x times delta p greater than or equal to h bar over 2. The uncertainty principle of quantum mechanics and the bandwidth theorem of telecommunications are the same equation, not analogous, not similar. The same. One is written in the variables of physics, position and momentum. The other is written in the variables of engineering, time, and frequency. But the mathematical content is identical because both are consequences of the Fourier transform. The Fourier transform imposes a trade-off between conjugate descriptions, and that trade-off has the same form whether the descriptions are quantum mechanical observables or engineering parameters. The bandwidth limit on your cellular connection and the uncertainty principle governing electrons in an atom are the same constraint. Fourier's constraint, derived from the same equation, applying at every scale from subatomic particles to global telecommunications networks. This is what I mean when I say Fourier did not invent a tool. He discovered a law about the structure of information itself, a law that governs how any system, physical or engineered or biological, can organize its description into complementary representations. A law that says duality the existence of two faces of the same reality, is not a feature of specific theories, but a feature of mathematics, of the Fourier transform, of the structure that Fourier uncovered in 1807, and that the world has been building on ever since. And the man who uncovered it never knew what he had found. He died thinking he had solved the heat equation, and in a narrow technical sense, he had. But the heat equation was just the surface, just the first application of something vastly deeper. The Fourier transform did not belong to the theory of heat. It belonged to the theory of everything, to every physical system, every engineering system, every biological system that processes information through the transformation between time and frequency, between position and momentum, between the signal and its spectrum. Fourier's equation is not a line in a textbook. It is the equation the universe uses to organize itself, and the fact that an orphaned tailor's son, studying by stolen candlelight, nearly executed twice, publicly humiliated by the most powerful mathematicians in Europe, managed to write it down in a prefectural office between meetings about road construction and swamp drainage, is either the greatest coincidence in the history of science or evidence that mathematics has a way of finding the people who need it, regardless of whether those people are the right kind of person for it to count. Let me tell you how this story ends, or rather, let me tell you why it does not end. In 1849, 19 years after Fourier's death, a bronze statue was erected in Auxerre, his birthplace, to honor his memory. It stood in the town square, a tribute to the orphan who had become a baron, the mathematician who had decoded the flow of heat, the administrator who had drained the swamps, the scholar who had catalogued Egypt. It stood for nearly a century. In the early 1940s, during the German occupation of France, the Nazis melted the statue down. They needed bronze for the war effort. The metal that had been cast in the image of the man who wrote the equation that would eventually run every piece of technology on Earth was liquefied and reshaped into shell casings or engine parts or whatever the German military needed that week. The statue is gone. The equation remains. And here is the final thing I want to leave you with, because it is the thing that kept me up while I was writing this, the thing I still do not know how to sit with. You are listening to this through technology that runs on Fourier's equation. The device in your hand, or on your desk, or in your ear is executing Fourier transforms right now, at this moment, as you hear these words. The compression that encoded my voice is a Fourier operation. The wireless signal that carried it to you is a Fourier operation. If you are wearing headphones, the noise cancellation is a Fourier operation. The screen you may be watching, if there is a visual component, is rendering a Fourier decoded image, and the neural signals in your brain that are processing the meaning of these words are electrochemical oscillations, frequency coded by the ion channels in your neurons, following dynamics that are governed at the quantum level by wave functions that are Fourier transforms of each other. Your experience of understanding this sentence is a frequency phenomenon. Your awareness that you are a person sitting in a room hearing about mathematics is itself a pattern of oscillations in quantum fields. The equation is not just around you, it is in you. It is you in the sense that the Fourier decomposition describes the relationship between every quantum state that constitutes your body, every electromagnetic interaction between your atoms, every neural impulse that constitutes your thought. You are a temporary, coherent pattern in the universal frequency spectrum, a localized excitation in fields that span all of space, a wave packet that satisfies the Dirichlet conditions and admits a perfect Fourier decomposition. Fourier did not know this. He could not have known this. He was solving a heat problem in 1807. in a world without electricity, without radio, without computers, without quantum mechanics, without any of the physics that would reveal the full scope of what he had done. He was an orphan with stolen candle wax and an equation that the establishment said was wrong. The establishment was wrong, and the equation is still running. In your pocket, in your walls, in the air, between the cell tower and your phone, in the MRI machine at the hospital down the road, in the LIGO detector in Livingston, Louisiana, listening for the collisions of black holes, in the satellite overhead, synchronizing its clock, in the seismograph under the ground, waiting for the earth to move, in the atoms of your hand as you hold your phone, in the photons striking your retina as you read these words, in the quantum states of the neurons firing in your brain as you try to decide what to make of all this. Fourier wrote one equation. In 1807, in a prefectural office in Grenoble, between meetings about roads and swamps, and the universe recognized itself in it. Every technology we have built since has confirmed what he found. Every experiment we have run has deepened it. Every screen and every signal on Earth is a testament to the thing he discovered, and the thing Lagrange tried to bury, and the thing the committee refused to publish, and the thing the Nazis melted into bullets. The equation does not care about any of that. The equation does not care about politics or prestige or noble birth or institutional comfort. The equation is true. It was true before Fourier wrote it down. It was true when Gauss discovered the fast algorithm and did not bother to publish it. It was true when Lagrange said it was impossible. It was true when the committee refused to print it. It has been true for as long as the universe has existed, running silently in the structure of matter and energy and light, waiting for someone to notice. An orphan noticed, and now it runs the world. And the world you experience right now, the solid, bounded, object-filled world of things in places, that world is the position space description, the Fourier conjugate description, the one in which you are not a thing in a place, but a pattern in a spectrum, is equally real, equally complete, equally valid, and the only thing connecting the two, the only bridge between the world you see and the world that is actually there, is the equation of a 9-year-old orphan from Auxerre, who studied mathematics by candlelight he scraped from the garbage. That equation is running in your hand right now, and it will keep running long after this video ends, long after you put your phone down, long after you forget the details of this story. The Fourier Transform will still be there, translating between the two faces of reality, running inside every device, governing every quantum state, connecting everything to everything through the secret analogies that unite the most diverse phenomena. Fourier saw the pattern. He wrote it down. The world suppressed it, and then the world built itself around it anyway. The equation does not need your permission. It does not need institutional approval. It does not need a committee report or a Grand Prix or a statue in a town square. It just runs.